we begin by giving the definition of a linear transformation. And remember, this is an abstract concept that we're going to define now. We're going to then see lots of examples of the diverse array of places where these properties show up in math to motivate why we abstract it into this definition. So first comes the definition. A linear transformation. A transformation means function. Function. And so we're not talking about sets anymore like we were with vector spaces. We're talking about functions between vector spaces. So if we're talking about a function between something other than a vector space, then it doesn't make sense to talk about a linear transformation. So we first need linear spaces, and we call those V and W right over there. We say t goes from V to W because every function has a domain and then the codomain, or where it maps to. You could also call these linear mappings. You could call these linear operators because it takes in a vector from V and spits out a vector in W. It's possible for W and V to be the same space, and sometimes we could say let T be a transformation from V to V, or from V to itself. But in general, the input space does not have to be the same as the output space. They just have to both be linear. And now, here are the properties that linear transformations must have. There are two of them, and they can be thought of as linear transformations preserve the linear operations. Remember, the linear operations for vector spaces were vector addition and scalar multiplication. And so those two conditions, right about down there on the page, those two conditions, one is that if we add x and y as inputs to t, then we can also then, or should also then, add their outputs. The t of x plus t of y, those are the outputs. And then the one beneath that with scalar multiplication, if we do alpha times x, or scale by alpha to the input, x, then we end up with the result that is scaling the output, t of x. The alpha moves outside. So there are, again, lots and lots of things in math where we can take some operation or some function of two things being added together and break it into the sum of those things. And same thing within math. There are lots of operations or things that we do where a constant on the inside can move to the outside. So here's the whiteboard that I have for this, and here are those two equations that I just described. We can take t of two things being added together, like t of a big thing, two things being added together, and break it up into two smaller t's, or two smaller parts. We can do t of x and t of y individually and add the results. And so adding the input is the same as adding the outputs. And here's scalar multiplication. We can scale the input, but the result would be we scale the output. So these are the axioms, two axioms that define linear transformations or functions from vector spaces that are linear. Remember in vector spaces at the beginning of this chapter, how many axioms were there to define a vector space? That's right, 10. 10 axioms. Here we have only two. These two should definitely be memorized. There's no rhyme or reason for these other than they're commonly accepted, and that's the motivation is that they show up everywhere. Here's an equivalent single equation or single condition that represents both of these together. And you can show mathematically, or you could prove that if these two things are true, then this one would be true. But you can also prove mathematically that if this one is true, then these both are true. And that's a good exercise that might show up on the homework, would be that proof. It's just a matter of picking various things for alpha and beta. Notice if alpha and beta are both 1, this simplifies to the first one. And there's a way to choose the alpha and the beta here so that this would simplify to the second one. So here's one condition that is equivalent to the two conditions. When it comes to proving whether a transformation is linear or not, we like to use this one because it's just one condition. Just one condition. So remember also in the notation in this class that the lowercase letters that you see on the whiteboard represent vectors. We use lowercase letters for vectors, and we use Greek letters for scalars. So the alpha and beta are always scalars, which could be like real numbers or complex numbers or more general fields. And then the x's and the y's always represent the vectors. Notice that on the left side, x's and y's are inputs, and so these are vectors in V. We make these statements for all possible inputs from V. Notice there's never there's not a symbol in here that comes from W. T of x comes from W, but I claim that that's two different symbols. And so these statements, the subject of these statements, are x's and y's and alphas and betas in V, or in the scalar field, respectively. Here's a picture to represent this definition, and I think the picture communicates in a different way, with a different kind of power than the algebraic equations. The picture is, let's consider the x and y, two vectors, in V. This is all V. So if we have two vectors in V that are a vector space, we can linearly combine them, do an alpha x plus beta y, and we would get a new vector, z, that's in the vector space. And for a function, for t to be a linear transformation, means that if this is what's happening in the world of V, in the vector space V, then if we map each one of them, x becomes a, like t of x is a, t of y is b, and t of z is c, then these vectors would have to be related in the exact same manner in W, in the world of W, and that is that c, the new vector in W, would have to be alpha a plus beta b, just like its input z was alpha x plus beta y. So we have to have this relationship that we call linear operations are preserved. And that's the definition, or why we call these operators T linear transformations. Because the linear combinations, the plus and the timeses, the scalar multiplications, the linear operations are preserved between the inputs and the outputs. The most grown-up name that we have for that, that's actually at the top of page 1 on your handout, is homeomorphisms. Homeomorphism. The word homeo means the same, or preserving the properties, and morphism means transformation. So a linear transformation, also called a homeomorphism, is a function between a vector space and another vector space, such that these linear operations, linear combinations, are preserved.